In this video, we are working on equipment at mains potential. If following along, please remember you do so at your own risk. Join me in my journey testing this Amiga 500 power brick, making sure that its output is still within specification, and then we can have confidence in plugging it into our Amiga 500 and enjoying this nostalgic piece of history. Amiga 500 power brick. This one's had a bit of a hard time. It's been dropped. There's a bit of a crack through here. This is my worst one, so I want to try and see if I can salvage this. Okay, there's a bit of a piece missing in the corner. Now, I haven't powered it on. I have taken the screws out so I can take the top off, but I haven't actually powered it on yet to see whether it still works or not. The inside looks reasonable. Can't see any. Well, looking down inside the secondary circuitry there's about four caps that I can see, electrolytics, and or five actually. None of which seem domed or in any sort of state where I'd be concerned. L296 looks like a regulator IC up the back there. I might grab the data sheet for that and have a look. But that all looks good. Look at the trimmer caps for, variable resistors for, I guess that'll be fine adjust on your power rails. What I want to do is fire it up, see if it works, see if we've got some sort of output, and then put the output across the oscilloscope and see if there's any noise or any sort of jumping around on the power rail. Make sure it's clean, because I don't really want to plug it into the Amiga if it's not going to be clean. So yeah, this looks promising. This hasn't been powered on for years, so I'm pretty sure that caps are all discharged. On top of that, there is no large storage caps on the primary side. I've got no concerns there. It's not like a switch mode. This is a linear regulated power supply. Yeah, the bottom of the transformer. That's the high side. That's all it is. A couple of caps there. Diodes. Looks like a half. Is that a half-wave rectifier? What will I be? It's a half-wave rectifier. There's only two diodes. Issues looking at all the tracks. The tracks look like they're intact. There's no heat marks, so can't complain, I guess. So there's no real reason why this wouldn't work. Let's see where the regulator IC is. I'm gonna go get the data sheet for that, because I'm keen to see the pinouts, and then I'll get some idea how this circuit sort of works, and I know how to trace certain things. I can't find a schematic for this power supply, although I've spent about 5 minutes looking. STP-110 Rev 1. Might give that a crack and see if I can find something. It's fairly simplistic from a circuit point of view. But yeah, interesting. So we'll do some testing, make it safe, and have a look at analyze the outputs and see how clean they are, and we'll go from there. All right. I'll set up for testing and we'll be back. Okay guys, I'm going to have to stand corrected because this is actually a switching power supply. The L296 that's up the back, I don't know if you can actually see it, or where are we? Up the back in here is a switching regulator. It's a ST microelectronics switching regulator, and obviously these are the inductors. So it is an actual switching regulator. So that's even more important for testing whether or not we've got clean, properly filtered DC coming out, because the caps are going to be key to making sure we've got that clean, well, clean-ish to a certain degree, DC output. I will most definitely be putting the oscilloscope across the outputs, and we'll see what sort of ripple we have. Hopefully the ripple's really low. I've got the spec sheet for this power supply. I will go back and refer to that and see what the ripple's supposed to be, or what the spec is, and then see if we're still measuring within that. I'll be very surprised to see a 30-year-old, well, what is it? Well, yeah, 30-ish year old power supply, and what time has done to it. Very interesting. All right, well, let's get set up. What I will do, I'll just solder some little pins on the back of the motherboard here, just power board here temporarily, something for me to hook onto with the oscilloscope, and then we'll go through and measure all the outputs. So I believe what we're dealing with is a black, brown, red, and a white. What's the back say here? We have a signal ground shield ground, 5 volt, plus 5 volt, plus 12 volt, and a minus 12 volt. The trick will be also is to load up each rail and see what happens to the output, whether or not we have increased ripple according to the load that's applied to the power supply. So this will be a quite interesting little test. All right, we'll be back. Just solder some pins on the back of here and we'll get started. All right guys, we're back at the test bench again. We've got, as I said earlier, we've got these test points I've soldered directly onto the voltage rails, power rails out of this power supply. We've got the ground. Actually, I'll get something better than this. Use this pencil. This is the ground pin, plus 12, minus 12, plus 5. So there's a few tests I want to run through today, and that is whether or not what the overshoot is like or undershoot on a turn on. So we'll turn the power supply on and measure the each voltage rail and see if it overshoots or undershoots, or see if there's any issues there. That's a pretty good indication of the overall health of the power supply. And we'll also check for the ripple voltage on each of the power rails with no load and with the rated load applied. So according to the case of the power supply and the spec sheet, I do have a spec sheet here, probably can't read that, I'll flick it up on the screen. The ripple voltage for the 5 volt rail is 50 millivolts, and the ripple voltage for the plus 12 and the minus 12 rails is 120 millivolt respectively. So we will check that out and go from there. I would suggest that the ripple voltage is measured peak to peak. It doesn't actually say here. Yeah, it doesn't say. It's just 50 millivolt, 120 millivolt, and doesn't designate whether it's peak to peak. But we will be looking at the peak to peak voltage anyway. Output current range, which is surprising, well, interesting. The 5 volt line says minimum output is 0.75 volts, so 0.75 amps, so 750 milliamp, up to 3 amps. Now, the power supply case itself says 4.3 amps for the max. So I'm not sure why they don't speak the same language. I mean, this does say Rev E. So I'll just cover this. Oh, this is getting dangerous. No, I'm not going to. It's the revision number is slightly covered with red tape, and the red tape here is covering the primary side, so all the high voltage stuff. So I don't want to accidentally bump that with my hand. So all this here is all the secondary low voltage side. Yeah. So interestingly enough, the plus 12 volt side, according to the case, is 1 amp for the plus 12 volts, but on the spec sheet it says 0.5 amps, so only 500 milliamps. Really weird. Again, I put it down to being it may be a different revision, but we will test it as per the plate on the power supply. Whoops. Yeah, so we'll run all the tests. And the minus 12 is 0.1 amps, so 100 milliamps. We will test all that as per this label and see how we go. I will do a test with, actually I didn't think of this earlier, but we can do a full load turn on test and check for overshoot and undershoot and all that jazz. But I think for now, what we'll do is, maybe first off we'll measure ripple. So what we'll do, we'll set the oscilloscope to AC coupling, because we want to measure ripple, and we don't want our line taking off on the screen. So AC probe times 1, that's fine. Now we want to change our voltage to, what's that scale that they're asking for? 120. So we'll go to 100 millivolt on the scale, and we'll look at, we'll try 100 milliseconds. Okay, so let's do this. No load ripple. We will connect ground to ground, and we'll start with our positive 12 volt rail. It's 100 millivolt, and we'll turn it on. Okay, so currently that's showing 8 millivolts. Let's screw down the scale a bit, 20 millivolts. Yeah, 5.6 peak to peak. So about 6 millivolts peak to peak, no load. About that. If I have a screenshot, I'll throw it up on the screen now. Okay, that's the 12 volt. Let's go to the negative 12 volt. So I'll turn this off and we'll turn it on and start again. Power supply on. Okay, let's shorten that scale down to, here we go, 200 microseconds. So our no load peak to peak is sitting around 15 millivolts, which is pretty clean, really good. Okay, now we'll look at our 5 volt line, 5 volt rail. Our 5 volt rail is sitting at 20, well let's call it 20 millivolts peak to peak. I'm happy with that. Alright, this is where the truth comes out. Just changes to that. Changes to that there. And we'll put our load on. So positive to the output, ground to ground. Turn the load on. Wait for it to set up. See if you can see that. Can you see that? Oh yeah. See if it'll come in. Okay. So we want to set our voltage to 12 volts. This is just our cutoff voltage, so if we go under, it'll turn off rather than damage the device. And we want to set our amps. Now the 12 volt rail is 1 amp max according to the case, so we'll go to 1 amp. And then we'll hit run. Oh, so much noise on the oscilloscope. Okay, our peak to peak millivolt, let's scroll down a bit. I'm going to call it at 145. So our plus 12 scale is supposed to be 120, but we're seeing 145. Slightly out of spec, but is it enough to, you know what, it's probably worthy of a recap. If we do a recap, we may see that the ripple and noise will drop off, but yeah, we'll see. So that's at 1 amp. So that's full load for the 12 volt rail. Again, 145 millivolts. So we're out of spec by about 20, 25 millivolts. Okay, so we'll go on to the next. So we want to swap the polarity around on the negative 12 volt rail. So our positive output, our main output is negative, and our ground is positive as far as the negative 12 volt rail is concerned. Put that on there. So we're looking at 12 volts, and we only want a 100 milliamp load as per our max on the case, the PSU case. So we'll screw that down to, oh okay, this dummy load only goes down to 200 milliamps. So we'll test it at double the rating. Hopefully we can pass out at that. Okay, double the rating on the negative 12 rail. Go. Well, coping quite nicely. And we do have a little bit of movement. Okay, our load is double the output, rated output of 100 milliamps. We are currently loading up at 200 milliamps, and we have a peak to peak noise level of about, okay, if we average it out, we're probably looking at about 8 to 10 millivolts. Can't complain. That's not too bad considering this power supply is 30 years old. Okay, so that's the negative 12 rail. Now we can go to plus 5 rail. So we'll swap these over. That will go to there, just like that. Negative there, positive here. Stand the dummy load up. Okay, we're going to change our load to 5 volts, and this is the big one. From a wattage standpoint, 4.3 amps at 5 volts, so we're already talking over 20 watts. We'll screw that right up to 4.3 amps, 5 volts, let's go. 5.05 volts, so it's maintaining over 5 volt, which is nice. And our peak to peak noise and ripple, we are looking at 120 millivolt. So we're on spec. So actually bouncing around between 116 and 120 millivolt. So we're on spec for the 5 volt rail. Impressive. 30-year-old power supply. Considering I haven't got the best electronic load, but I think it's doing enough. Let's just bump this up to 4.5 amps. Well done with the 6. Let's go 4.5, and we're sitting at 120 millivolts to 124. I'm going to call that in spec. I'm not going to be too concerned about that. Yeah, love it. The heatsink is getting slightly warm. Can't complain too much about that at all. So I'll put this over here and hold this up a little bit. Get the old multimeter out. Just measure that 5-volt rail. Negative, ground, and the positive. That's 5.2 volts at full load. Can't complain. What would it be at no load? Let's just turn this off. Whoops. That's not bad at all. That's regulating beautifully. 4.5 amps straight up, 5.2. You gotta love it. Gotta love it. Well done. No complaint there whatsoever. Okay. Let's test for overshoot. So we'll turn this off, turn the power supply off, unplug everything. So what we want to do now is see what happens when we turn the power supply on. So the reason why we test for that, on the Amiga, each power rail, when you first initially turn the power supply on, you can't go over a certain voltage. And in this case, I don't really want to see going over the rated voltage. Per the power supply. So if it's a 5-volt, you don't want to see any overshoot over the 5-volt. Same as for the 12-volt. Then we'll go and hopefully, if that works out well, this power supply is a good candidate to plug into the Amiga that I have without risking damage to it. And we can test out our cable that we've just made, and we can test out the memory expansion real-time clock card that we've just modified. So that'll be an absolute win if we can get that done. So let's give it a shot and see where we go. So we want to turn single shot capture on. We'll start with that 12-volt rail. We'll change our voltage scale to 5 volts per division. So that means we'll get roughly 2 point-ish gradicules per 5 volt. Hopefully we can maintain it in the shot. We'll turn our scale down to about 100 milliseconds, which should be a good window to capture a turn on. And we will set our trigger to, well, our 12-volt rail is 12 volts, so we want to set it to about 11.5. See if we can trigger on 11.5. Okay, so single shot capture. Power supply is currently off. Let's turn it on. Ooh, oh, why did it turn straight off? Have we got an output or not? No, we have. Oh, I'm an idiot. Got AC coupling still on. It's a bit of muntage in my brain right now. Right, let's try it again. So single shot capture, power supply is off, give it a few seconds to discharge, and we'll go from there. So ready? 3, 2, 1. You can't get, oh, you gotta see this. You have to see this. I'll move the camera. See if you can see this, guys. Look at that waveform. What? That is clean. The power supply is 30 years old. Oh my God. No overshoot. No ringing, no undershoot. They don't make them like they used to. They really don't. They really don't. Okay, that's the plus 12 rail. Let's see if we can change over to the minus 12 rail. Minus 12, we'll have to change our trigger on a falling edge. Oh, it's already set the falling edge. Interesting. It might reset me. Okay, we want to go to negative 12-ish. Let's go negative 11.5. Shits and giggles. Okay, 11.5. Our power supply is currently still on. Let's wait for it to settle. Turn single shot. Okay, good. Single shot is on. This is the negative 12-volt rail. Let's go. Again, perfection. No undershoot, no ringing. Absolute perfection. You can probably see that on shot. Yeah, you can. Wow, amazing. All right, let's go to the 5-volt rail. Now we're in the 5. We'll wait for the power supply to discharge. Shouldn't take too long. Give it a few seconds. Okay, what I'll do now is change our scale to 2 volts per division. Give us a bit more resolution in the capture. Okay, let's go. Oh my god, same again. I think you can see that in the shot. It's just amazing. I'll have screenshots of these anyway, and I'll put them up on the screen. This blows my mind for a 30-year-old power supply, and I haven't done anything to it. Apart from soldering these test points on, I have not done anything to it. Super impressed. The chair's a bit squeaky. Okay, so our third series of tests we want to do is power on under load and see what it looks like. So we'll leave the setting for the 5 volt there for now. Oops, pops off. We'll get it underneath. We'll get our load out. Now this 5 volt rail is good for 4.3 amps. Okay, so we'll set that up for 4.3 amps. 5 volt, 4.5. Let's just do it at 4.3. Turn it on. Okay, no volts. Of course there won't be. Can we turn the volts to 0? May not be able to turn this on because it needs to detect the voltage before it will activate the run. So we'll turn it on at the same time. Oh, single shot capture. No. I actually can't do that. Can't turn it on. Huh. Oh, you know what? The trigger's set wrong. We need to set the trigger to about 4 volts. It's about 4.5 volts. 4.48 on. Whoop, single shot. Let's go. Wow, even with load, now I can't complain about that. No overshoot. Looks like there is overshoot, but there's none. Impressive. All right, that's enough testing. I'm going to button this one up, box it, and see if we can fire up the old Amiga. Exciting times. Can't wait. Can't wait. Righto guys, see you when we have the Amiga all set up and ready to power on. I hope you enjoyed my video. Don't forget to subscribe, like and comment. Click the bell icon to get notified of any new videos. And thanks for watching.